sift, wash, find, grind, star garnet. It's pretty simple. What's left to talk about?
Well, we should have gotten this before, sorry. This will be, everybody will understand this perfectly. I started here in 1989, and I was very lucky to end up here and spent my whole career here, not imagining a better place on the planet Earth to be for lots of reasons. One, for example, the star garnet.
It's how I got into geology, actually, in the late 1960s. I was raised in Moscow, so it was local. My dad and I were rock hounds, and so we would go up there and dig before there was a Forest Service dig.
What we do out there while the contractor is mining the material is that we'll take samples and test material from the different, excavator scoops. And so we might take a little shovelful, go wash it off, and just make sure that they're actually in some garnet-bearing area. We
suggest that people bring in everything they found, and then we'll just sort through it and pull out the stuff that looks good. When we do this, we'll do that no charge. We can test those, and we charge $10 to test a star stone. And at that point, we can be fairly certain that we'll find something. We don't know if it's going to be good, but something.
So those are almandine garnets, pretty common variety, really. It's just that these particular ones in Idaho have got little rutile inclusions in them, little titanium-bearing minerals that are concentrated particularly in the cores of them, and that's what ultimately gives the star.
When cut, it can form bands of light through it, just like a star. An asterism is what it's called in stones.
Asterism in general is a streaking effect, you see. And one of the first places I ever really noticed or thought much about asterism, I had to rent a car. I was driving in the car after dark in the rain, and the windshield wipers, when they'd go across the windshield, I'd see this streaking effect. And the streaking effect happens because there's dust in the air. Dust contains quartz. Quartz is harder than glass, and given a no windshield, it'll produce this singular streaking. So the streaks in this direction make asterism in this direction. And what I noticed in the car windshield, where the windshield wipers crossed, the asterism was flipping. So that was sort of my first literally exposure to asterism. We had maybe seen it a bit as a student, but never really paid attention to it. So that sort of effect stayed with me for a long time.
Almandine, the Forest Service, rutile, asterism. We'll discuss all of these with experts in the fields of mineralogy, geology, and lapidary arts. But first, let's take a step back and talk about garnets. Garnets are everywhere. They're a group of minerals common in metamorphic rocks and occasionally igneous rocks. Note I said group of minerals and not the mineral garnet. The term garnet refers to a group of minerals sharing a similar structure. Most people think of this when they think of garnet, which is fair, and after all, the word garnet comes from garnet, meaning dark red, possibly deriving from the Latin granatium, relating to the seed of a pomegranate. Consider almandine your gateway to the world of garnets, which is more like this, where a wide range of colors and hues are possible depending on the composition. The different species of garnets are almandine, pyrope, spessartine, grossular, uvarovite, and andradite. So this is a garnet, and this, and so are these. And these species are just the end members, with solid solutions between some of them, creating, for example, the pyralspites and the eugrandites. There's also a garnet supergroup, where even the silicon can be replaced by other elements like vanadium, arsenic, and yttrium, but still be arranged in a garnet structure. Minerals are made of atoms that self-arrange in repeatable, predictable ways depending on environmental conditions of formation. Silicon links up with some cations and suddenly you have this. The cations, or positively charged ions, vary depending on the chemistry of the matrix, which is why there are so many varieties of garnet. When I said garnets are everywhere, I was mostly talking about almandine garnets, the eponymous red garnets. This iron-rich aluminosilicate species is the most common garnet type. I think it's a combination of how they form and their composition. Iron is common, and almandine readily forms from regional metamorphism of clay sediments. That's why in the US, they're concentrated near mountain chains and other areas of tectonic compression. Star garnets in the United States are primarily found in a small region in northern Idaho near the town of Clarkia.
So let me get oriented here. Okay. So all of this green right in here is all what we call the Pegan group, which includes the Wallace Formation. And then above that, stratigraphically, is what we call the lower part of the Missoula group, and that's this kind of light tan color here. And was called historically the Upper Wallace. And that's the unit that is clay rich. It was pretty muddy. And so that's the one that grows the garnets. And so you can see here's the St. Joe River flowing west here. And you can see all that upper St. Joe area has got the lower Missoula group, upper Wallace material. But then it also comes down around into here, and then we're getting down to Clarkia, which is right in here. And this little piece right here of the light colored is the material in the Emerald Creek area with the garnets in it right there. And the garnets are basically south of this line. There's a little white line on this map. That's the garnet isograd. Comes along here, comes along there. So basically, garnets this way, same rocks to the north, but no garnets growing in them. So there's higher metamorphic grade going south.
There's a couple of ridges where we found these garnets, but the garnet belt itself is much more extensive. And I can't speak to whether any of the garnets, like to the east of here, there's a lot of garnets east of Clarkia that I've heard of, other rock hounding sites on BLM property and stuff. I do not know if those have stars or not. I have not heard that they do. But to my knowledge, the star garnets are kind of more concentrated in a smaller area. And then the garnet zone is much more extensive and goes south all the way to the Nez Perce Clearwater Forest. That's our southern neighbor, and there are garnets down there too. So there's just a lot of garnets in Idaho.
You can find garnets in that same formation of the belt supergroup all the way up the St. Joe River and tens of miles away. But those are really small, and I've never heard of any stars that far away. It does seem to be sort of in that Emerald Creek Clarkia area.
One of the interesting things I've heard about the geology here is that Emerald Butte and Bechtel Butte, which is the neighboring butte, they are actually anticlines. And the closer you get into the apex of the fold, the larger the garnets are. So that's one of the things that I've heard from people who've actually mined into the rock in situ.
Generally, you need to get the rocks down deep, so you can either you can either thrust some material up and over them and then bury them. It doesn't hurt to have magmatism also, but we really don't have any known magmatic events, certainly not at the 1.1 billion year age. So it's still a little bit of a mystery.
It's been buried and metamorphosed. And if you go to Wallace and look at the outcrops there, you can see, just this plain old rock. I think what I've heard is that there's some carbonates in the Wallace, but it's mostly just like siltites and argillite and some quartzite. But you bury it and cook it for long enough and you can get garnet schist. And so that's what we have here.
Traditionally, it was known as the Upper Wallace Formation. More recently, we've realized that it's equivalent to some rocks in Montana. They're called snow slip. It's a really old sequence of sedimentary rocks. It's really widespread. The rocks you see in Glacier Park, all those nice flat layered rocks, that's belt supergroup. The lower part of it was formed in a rift basin that was pretty deep water. So you had the continent was rifting apart, pulling apart, and then the sediment was coming in from all sides or several sides, and then that's kind of filled up. The rifting slowed down, it filled up, and so then you had sedimentation that was in shallow water, and that's about the upper half of this sedimentary sequence, and it's tens of thousands of feet thick. It's really, really a thick sequence, and it started like 1.47 billion years ago, and lasted at least till 1.40 or a little bit less than that. So a long period of sedimentation, and Some of it is mostly it's like a fine sand, but there's also clay-rich zones, and those are the ones that have enough aluminum in them to form the garnet. So you need a sandstone. No matter how much you metamorphose, it will never make you a garnet. It's just too much silica and not enough iron and aluminum in it, and magnesium. So it's really the things that were originally clay-rich that really form the garnets, and so that's not very common actually even in the belt supergroup to have like a big thick section of rocks that were clay-rich, but that particular zone around Clarkia does have that. We call those, if they're not metamorphosed at all, we call them argillites. But once they get a little bit metamorphosed, actually to a level of growing micas, then you have a mica schist. And so you'll have a garnet mica schist up there, and that particular unit just grows garnets just beautifully. It's pretty much anywhere in that region you can find small ones, in the whole St. Joe, Upper St. Joe drainage, for example. But it's really only around Clarkia that they get very big. This is the Potlatch 30 by 60 quadrangle, and this is Bechtel Butte right here. This is Emerald Creek right here. So the Emerald Creek diggings are right in through here. No Name Gulch and so on are these guys right here. And this slightly more brownish green is the schist, the Upper Wallace / Snow Slip schist that makes the good garnets. And then this is a more carbonated and sandier unit, and there's really no garnets to speak of in this unit right here. And then this is that garnet isograt I was talking about. So everything over to the east of that line and to the south of that line have garnets if you have the right starting composition. And then off this way, you might, like this unit right here, the Libby Formation would have made great garnets, but it just never got metamorphosed enough.
A lot of it is private. A lot of it is private forestry. Some of it is state. Some of it is BLM. And a lot of it is Forest Service acquired land in which the BLM owns the mineral rights. And so those are closed to mineral entry, and you cannot stake claims or rock count on those lands without express permits and permission from the BLM. And so that's kind of why, another one of the reasons why this site is so unique, because we are providing an opportunity for people to get a resource that really is not accessible anywhere else.
See these little fine layers here? That's the original sedimentary layering. And then these little reddish guys, those are the garnets right there, right here. And the kind of sparkles, that's mostly muscovite, which is a white mica. Getting the garnet ages is very time-consuming. It's a very difficult process. It's done over at Washington State University, Jeff Revort's lab over there, and it's slow going. And so it's isotopic methods that just take a long time. So we don't have a lot of data points. The initial garnet growth looks to be about 1.34. So there's enough time there, to get buried and to grow garnets, and then there's another garnet growth at 1.0 or so, 1 billion, and I don't know the proportion of how many garnets we're seeing out there, which.
Nobody's determined when the placer deposits were formed, but the stream might have shifted during the Miocene when Columbia River flood basalts poured in and messed up the drainages in the area. Either way, they sat relatively undisturbed for likely millions of years. The story goes that in 1937, the first Idaho star garnet was found near Clarkia, Idaho, in Shoshone County, specifically along Emerald Creek by a logger named Ed Sexton, whose nickname was Shorty. He would go on to obtain a mining claim and name it Shorty's Diggins, operating tens of acres as a feed dig starting in 1966.
There was Shorty's, but that was a private setup, really on a different location, one single location. And he had some really, really nice material there.
In the old days, from the 1970s onward up until the early 2000s when we switched over to stockpiling the material, the public could come to the site and purchase a ticket on site from the A-frame. There would always be a Forest Service personnel down there who would, take your money and issue you a ticket on the spot, and you could dig in the creek itself, in the gravels of the stream. And so the 281 Gulch is the one that we're next to here. That's the old site where, the public used to come and be able to dig their own holes.
And at that time, then people were just digging everywhere, sort of helter-skelter, digging under the banks. It was pretty dangerous, actually, in some of the areas that they were excavating. And they were also digging right in Emerald Creek itself, not just the tributaries.
This site has been in operation since 1974. The land was private land before it came to us in the 1960s for the express purpose of making a site where the public could come for garnet collection.
So then I think it was the early 70s, mid 70s when it was closed off and then regulated. And so I used to go up there quite a bit, I would say through the 1970s and dig. And basically in those days you would dig a hole straight down and hopefully you would be digging where nobody else had dug, which is not always the case. And then you would get the material down in the bottom there. They're heavy. It's heavy, just like gold is heavy, so you want to get down low near the bedrock, or as low as you can get, and then put that in a screen, wash it, put it out on the bank, especially if it's a sunny day. You can see the garnets with a purple color and basically just, pick them out. So here's a classic. Here's me, there's my sister, and there's my dad. That's Glenn Lewis, my sister Ann, me, Reed. And there's my little sister Amy. And this is up there digging for garnets in 1970. And I'm not even sure exactly. That must be it's not up one of those gulches. So that has to predate the Forest Service stuff, I think. So
That's quite a bit of history.
yeah, and then I've had this since then too. You should need to take a picture of that. To be honest, I haven't been up there for 20 years or more, something like that. So it's my understanding now that you don't do the digging, the Forest Service actually scoops out material, and it's a little bit more organized now than it was when I was a kid.
We switched to doing the excavation ourselves and stockpiling it for the public to come and take the way we have it here now because of resource damage that was happening, aquatics, there's fish-bearing streams that were being impacted by the heavy flow of sediments from the operation in the streams that would be, all summer long. You have 5 months of sedimentation, digging, and destruction. And so there was that piece, but there's also the safety aspect as well. The garnet zones could be quite deep, 8 to 10 feet sometimes, and people were digging these very deep holes. There was no shoring, there was no safety precautions, and it just became kind of a problem that we needed to address. And so then the other aspect of it is that there's garnet still left in the ground because there was no methodical excavation. And so resource damage, safety, and actually being able to provide, to deplete the resource. These are all things that kind of contributed to the decision to move to this new format. .281 Gulch was depleted and reclaimed, I think, around 2017, 2018. We started the new excavations in Garnet Gulch, which is now where the material is coming from, and we started that. The first excavations there were in 2019, and so far we dug in 2019 and 2022, and that material is still being is still provided here. We haven't needed to replenish the stockpile.
There are other private claims in the area, and most are not open to the public, and not all of them have star garnets.
Here we're dealing with larger size garnets, right? The sieves are, I think, 1/4 inch. So people are looking for 1/4 inch and bigger garnets. Downstream, where these streams all go into Emerald Creek, and there are garnet sand mines, commercial garnet sand mines at the distal end of Emerald Creek, and they mine out the garnet sand, which is used in industry for oil and gas, use it for fracking, and then it's good for abrasives and water jet cutting media and stuff like that. So yes, the actual little tiny garnet sand sized particles are also valuable.
Although not all garnets in the area will star, there are still high-quality garnets that could be suitable for jewelry or faceting. For decades, Louise Starby offered guided digging tours to her claims, educating visitors while also sending them home with ample garnets. Although retired now, she earned the nickname of Idaho's Garnet Queen thanks to her outreach, keen eye for quality material, and skill in working with the gemstones. Now, if the Forest Service site is booked or it's out of season and you don't know anybody with a claim or property around Clarkia, your best bet is the Huckleberry Garnet Mine. They pile up ore that you dig and screen yourself, only charging a small fee to dig and then a per ounce charge of workable material. They also run the Fossil Bowl, a fee dig site for Miocene epoch fossils, mostly leaves. I believe their Huckleberry Garnet ore comes from the nearby Bechtel Butte. Which brings us to...
Bechtel Butte is mostly Forest Service acquired land, and so the garnets that are on Bechtel Butte belong to the BLM. And so in order to prospect them, you have to have a prospecting permit. And most of Bechtel Butte is already under prospecting permit applications. So there's not really rock hounding opportunities for those garnets. They are dealt with differently than on public domain lands that are open to rock hounding. It's pretty much closed to that activity because of the status of the land and the status of the mineral rights not belonging to the public.
At Bechtel Butte and some other local claims, the garnets are in situ. That just means the garnets are found in the host rock where they formed. At the Forest Service dig and the sand diggings, they're essentially placer deposits. The garnets here were eroded out of their host rock and transported by Emerald Creek and deposited in gravels when the stream followed a different path through the mountains. The region of Emerald Butte that was the source of these high-quality garnets is now likely gone, eroded away completely. Don't get me wrong, though, there's still lots of garnets in those hills, at least 8 separate localities. But that doesn't mean you should just grab a shovel.
We encourage people to come here. There's another fee dig site that people could go to. We discourage people from going and hunting for garnets anywhere on Forest Service acquired lands. And if people want to know where those are, we do have maps, and they can always contact us and we can give them information about where they can and can't rock hound. Because of course we don't want people running into trouble with law enforcement and whatnot. So
this isn't a gray area. Don't dig where you're not supposed to, and don't try to beat the system and dig at Emerald Creek site after hours or off season. You will be caught and fined. It's easy to say no digging, but you might be asking yourself, why can't you go up to Bechtel Butte? If you're like most rockhounds, you might pick up a book to find locations. Bechtel Butte might be in there. If you're more experienced, you'd look at land maps and see that it's part of the St. Joe's National Forest, and you know in Idaho you can do casual rockhounding on most of those lands. Digging deeper, there's only one pending mining claim on the butte in the BLM data viewer. Looks like open season. But here's the thing. Bechtel Butte and nearby areas are Forest Service acquired lands. If you're like me, you hear that and think the Forest Service just bought up some lands at some point. But the phrase is actually a legal definition referring to lands currently administered by the Forest Service which, 1, have never been part of the original public domain, or 2, had at some time in the past left federal ownership and have now been conveyed back to the United States. Because these lands were acquired and aren't part of the original public domain, that means that they are withdrawn, which is another legal classification referring to areas of public domain or acquired lands that are restricted to specific uses. So even though the Forest Service and the BLM generally allow limited rockhounding on their lands, that's not the case here. Look, it even points out acquired lands are an exception in the brochure. The BLM owns the mineral rights, but nobody can stake a claim on Bechtel Butte because they're closed to mineral entry. Don't expect this mining claim to be accepted. However, you can get a mineral prospecting lease, but that's not just casual rockhounding anymore, and it involves permits and fees. Plus, Bechtel Butte is already booked up. So yes, please believe me when I say that Bechtel Butte and other nearby lands on the St. Joe Ranger District are withdrawn from mineral entry or use, and therefore mineral collection is not allowed. For more information or to check if an area is open to rock hounding, please contact the Minerals Group of the Idaho Panhandle National Forest. Also, don't believe everything you read in old rockhound guidebooks, because more than one will direct you to dig illegally at Bechtel Butte or other incorrect locations. Instead, plan your visit around the Huckleberry Garnet Mine or make a reservation to dig at the Forest Service's Emerald Creek Garnet area. Either one allows for hours of fun.
Most of our star garnets come in from the populace who dig them at Emerald Creek, which is a Forest Service run mine. It's pretty easy to get there, get online at the Emerald Creek Garnet area website and make a reservation, go dig some stones, and then folks will bring them in here. We have a look and try and pick out the stuff that can be made into jewelry. It's a really great, really fun, easy access opportunity to just go dig, go to the Emerald Creek mine. Inexpensive and a great, like a really fun family opportunity, or even just individuals. And you will most likely find something that you can make jewelry out of.
Since COVID, the way that we started to do the site in 2021 was to have an online reservation system. And so you can go buy tickets online. And the way that works is that the ticket for a particular day goes on sale 3 months before that day. So if you want to go out to the site on August 1st, then you need to go buy your ticket and be ready to buy your ticket on May 1st. And then every day after that will go on sale exactly 3 months prior. And so that's how they're sold online. And I advise any day that you select, be online by 7 o'clock in the morning and be ready to buy your tickets, because they do sell out fairly quickly. We have 30 people in the morning and 30 people in the afternoon shift. You buy your tickets online, you show up with some ID, and you don't need to bring any tools. We provide everything. We have buckets and shovels. We have the big pile. You help yourself to that. Go to our sieve station and get all the fines out, and then you come over here to the sluice, and there's water running in the sluices, and you just pick out your garnets from your cleaned material. Once you come over here to the sluice, you wash all the gravel material, pick out your garnets. The fine washings go down into retention ponds, which get dredged out once every 2 weeks during operation. That material goes down to the A-frame where it's stockpiled, and that's used for backfill in the new mining areas. So next time we excavate, all that material, all the fines from here, all of the tailings that people dump over behind me, the gravels that they're rejecting, that they've hopefully picked all the garnets out of, that material all goes down there, and then it's used for backfill. So it goes right back into the same stream that it came out of just some years later. The site is pretty rustic. It's very remote. There's no cell phone service out here. The nearest town's about 10 miles away. That's Fernwood. There's a little grocery store where you can get provisions and stuff there, and gas if need be. But out here, it's pretty remote. There's no facilities other than, we provide portable toilets. We provide all the tools that you need, but it's pretty rustic. So just people should be aware that it's not, whatever accommodations they need, just plan ahead, get prepared, bring water. There's not going to be any water provided, so bring your own water, bring your own food.
Now, you can no longer show up and just buy a permit at the site like the old days. You also can't buy more than one personal permit per year, which means you have 3 hours per year to collect as many garnets as you can. The limit used to be 5 pounds per day, but was recently reduced to 2 pounds. The most I've found in 3 hours is just over 1 pound. You are allowed to bring non-powered tools like a homemade sifter. It's an uphill hike from the parking area to the dig area, so you may need a wagon if you have a big group with lots of stuff.
Our site does accommodate people with mobility issues. If that is the case, then, and somebody needs that accommodation, then they can actually drive all the way up past the gate, which is closed to the public, but we let people with the needs come up, offload, and then parking is down in the regular parking area. there's another fee dig place that I know of on the forest, not our forest. It's on the Beaverhead Deer Lodge in Montana. They have Crystal Park, which a lot of rockhounds will have heard of and probably visited. But that site, it's run a little different. You can go there and dig. Then every couple of years, they'll fill in the holes, cut down the hazard trees, and make it safe for people again. So they're not doing a stockpile situation, but it is a fee dig place on the forest. I have heard of a place in California where there's the rainbow obsidian. I'm not sure if they charge. You have to get a permit to dig there as well. So there's a few places like that on the forest where rock hounding is a little bit more controlled. But this is the only one that I know of where we mine, and then the public comes and gets to dig in the mine or in the ore pile.
The ore pile. Those who visited knows it gets taller the more hours you spend at the site, no matter how many buckets you bring down. But where does this Sisyphean nightmare come from? Well, it used to come from 281 Gulch, about 300 feet away, near the old A-frame hut. With that historical deposit depleted, they're now sourcing from Garnet Gulch further into the forest. Ooh, that one smelled fresh.
Huh?
That cow pie back there smelled fresh.
Yes, it's problematic for us. Okay, so do you see the pink flagging right there? That's the end of the last panel that we dug. And so they come down where you can see a little bit further. You can see there's trees right down there. From the trees to this pink flagging is what we mined last time in 2022. And so it's 3 panels. They're roughly 50 feet by 100 feet, 50 feet long, give or take. And the panel down there, the first one that we dug, we had to go down 15 feet to get to the Garnets zone. These panels, as we came upstream, were more like 8 to 9 feet down to get to the Garnet gravels. And then we came out and planted trees, so you can see them, little cedars here and there.
Where,
I'll show you.
yeah, I don't see it.
Oh, there's one right here. They're very little, they're babies. There's one.
Oh, okay.
So we planted 450 cedar trees, and that includes the further panels down there, which were dug in 2019. You can look at those too if you want. This is what it looks like after 2 years after we mine. And so you can see that there's some, grass and stuff growing, and things are stabilizing, which is what we want to see. The stream itself recut its own path. We did not make a pathway for it after we were done. We bypassed the panels while the stream gets bypassed while we're mining, and then when we reopen it, it just cuts its own path. And so that's what you're seeing here. And planting the trees is kind of the final step with trying to, get this site back to its original form.
And this is no longer part of 281 Gulch. This is a different
Garnet Gulch. Yep.
Garnet Gulch. Okay.
It's a lot of material that we're moving, and we kind of mix the overburden in with the garnet gravels so that there's a good volume for people to hunt through, and it makes it kind of fun to actually hunt and be challenged to find garnets. And so that's all we do. It gets stockpiled right away after that. This is sort of what the garnet material looks like, right? Down in that pile. After it gets mixed up at the stockpile, then it comes down here for its final destination, which is where the public comes and digs directly on the pile. And so it's a fairly quick and very dirty mining operation that we run. And our whole goal at the end is get everything out, backfill it, and get it reclaimed. And work on restoration after things stabilize. And so there's really not any opportunity for the Forest Service to do any kind of like partitioning of good quality material versus others. I mean, everything that comes out of the ground goes into that pile, other than a few samples that we take from the excavator to make sure that we're in the right zone. Because the excavator operator cannot see that he's in the garnet zone. So that's what we do. We help him, guide him. Okay, you need to go a little deeper. You're not quite in the zone yet. And then he can feel when he gets to the zone that it's a little bit different than the overburden. And then generally he'll be able to excavate that whole zone. And we just help with making sure that we're in the right, that we're actually getting garnets. In general, in northern Idaho and on the Idaho Panhandle, we pretty much are limited to garnets and gold panning. That's really our resources. However, we do have one site, and it's called the Solo Creek Quartz site. It's pretty popular. It's in some of the Rockhound guidebooks. That's where people can dig for quartz crystals. And it is public domain land. It is open for that. The problem is that there's a lot of damage at the site that has to be mitigated before we can reopen the site. So we closed it earlier this year. It's going to remain closed until we're able to mitigate those hazards. So there's hazard trees where rockhounds have dug underneath the roots of trees and killed the trees, and then the trees blow down and come down in the middle of a storm or wind, and it's a hazard that we have to manage because we know about it. And so what we're trying to do there is have the holes filled in, have the slope stabilized, cut down the hazard trees, and then once that's done, we'll probably do some planting, and then once things look pretty stable and good, we'll reopen the site. And with the understanding that rockhounds are going to, for the most part, be good stewards, fill in their holes, don't dig under tree roots, take out your trash, pack it in, pack it out, all that good stuff that rockhounds need to follow and generally do. You know, they've been digging out there since probably the 60s, maybe even before that. And so we're just managing it, and once that's managed, it will reopen for people. The damage there is a good example of what can happen when we aren't managing the land properly on our end. And one of the reasons why we do this site the way that we do, because again, it was the same sort of situation, very big holes, lots of hazards to navigate. One of the benefits of the way that we're doing it now is that the disturbance to the stream channel and the ecosystem is only 2 weeks long, because our contract that we have for excavation of the garnet material is from start to finish, from removing the topsoil, stockpiling it, and digging out the gravels, mixing it, and backfilling and reclaiming is all done in 2 weeks. We monitor the sites after the fact and make sure that things stabilize over time, and we plant trees. It makes it so that the amount of time that there's disturbance that might impact other resources like fish and hydrology, it's very short, and that's very beneficial. And so that's one of the reasons that we do it this way also, is to just keep that period short. And we get all the garnets. So once they're depleted, once they're taken out of the ground, there's not going to be any question as to whether you should go back in there and mine again, because we've mined it all. And so that's another one of the benefits, is just getting the whole resource out of the ground for the public.
They're known to be found in a place in India and here in Idaho, so they're fairly uncommon.
Only Idaho and India. Only India and Idaho. This great soundbite is ubiquitous in coverage of star garnets. It's also wrong, and worse, has been incorrect for over a century. Shout out to Mark Mouthner for leading me down the path to what might be the earliest reference to Garnet asterism, an 1891 Geological Survey of India report. They note asterism had been observed in a great number of Indian garnets. What's even more surprising, though, is that they're discussing star garnet from a schist in Ceylon, now Sri Lanka. So 133 years and counting of this being wrong. Minimum, because there must be an earlier reference somewhere. An argument can be made for the 1862 Manual of Mineralogy, where they examined a Sri Lankan garnet and noted, when the faces of the rhomboidal dodecahedron present two systems of cross striations, they offer by reflection to a bright light an asteria with 4 branches normal to the direction of the striations. That sounds like a star garnet to me, but a subsequent report argues that the manual was describing a different phenomenon in garnet and calling it asterism. Maybe something was lost in translation. Either way, it's time to retire the phrase only Idaho and India. I suppose only Idaho and India and Sri Lanka doesn't have quite the same ring to it, But at any rate, that's still wrong. Star garnet from Madagascar was reported in 2002, and there are also reported occurrences from Tanzania, North Carolina, and maybe Connecticut. Have you heard the saying that it's only Idaho and India have star garnets?
I've heard that as a kid. I heard that. I don't know if it's true.
I don't know the origins of that rumor. I have heard that Idaho and India are the only places where they're kind of in commercial quantities. I don't know if that's true or not. I've heard that there's star garnets from Madagascar, somewhere out east, maybe in the Carolinas somewhere. So for sure they aren't, this is not the only occurrence of star garnets in the world. It's just a very nice concentration of them. It's one of the places where the public can actually, it might be the only place where the public can come and have them pretty much served up, right? Without too much effort.
And we go out occasionally as a shop, just a kind of a group outing. Most of the work we're doing is customer stones. But, we have some that we can cut. If somebody comes in and wants something, we'll just go through our collection and find the best match.
So this is what we would find. This is the material.
So this is the 70s?
This is a 70s collection. And a friend and I went up one time, high school, and we hit a pretty good load. And he's got the biggest one. It's maybe just about a little bigger than a golf ball, something like that. And he kept that one, and I kept most of the rest of the others to polish. And we camped that night at the campground, Forest Service campground downstream from the dig, and we thought we were rich. We were gonna just retire on our wealth. Well, we tried peddling all these garnets, and it turns out we weren't really that rich because everybody, at least around here, already had their own can full of garnets and stuff.
I look for a piece of material that's not fractured, that's solid enough to work with. Second, like where it came from. Like really the best way to know if it's going to be a star is did it come from a place where that material all has the star material in it. And then just visually, there's some patterning, like they tend to be rougher if they're a better material. It's hard to describe, but it's more of something that over looking at thousands of them can kind of just have a better guess than I used to about whether or not there'll be a star.
You have to have pretty good crystal faces to see if there's like this sheen that you'll see on the surface, and that's kind of a good indicator that there might be silk that creates the asterism once it's cut. There's also the raisin texture, and I'm not sure what causes it. I think it might be from etching, some kind of etching or something. I don't really know, but the raisin textured ones also seem to produce stars. I don't know if there's really any correlation to that, but that's something that I've also heard.
Raisin appearance comes from having, traveled and broken up and that sort of thing. So yeah, that's exactly, and they do. They look a lot like raisins.
In order to actually test that, I would just split the stone and then cut a little dome into it that would allow the star to show if it's there.
Well, with the star garnet, I mean, the inclusions are what makes the star. And if you have a perfect perfect garnet, and it'll show you some at Gem State, hopefully. If you have one that's perfect faces on it, forget it. That's not going to make a star garnet. You want the ones that are sort of more gnarly looking. Those are the ones that will produce the stars. And, the ones that produce this star, if you then cut a diagonal this way, you get this star, imagine one like this, that's the 6-ray. Those appear to go where you need more inclusions. So you'll see this one, and then the inclusions increase, you'll see the one the other direction. But one thing you notice on them is the intensity of the asterism is not the same in all directions. And that's the way you actually see them in the structure.
It's the material that's the star, and so if you had a stone with the star material, you could break it into as many smaller pieces and still get a star in each of those pieces. So really it's a lot of times the star is the strongest on the center of the stone, and so you'll actually by default get 2 stars out because you want to be splitting that down the middle and then get a star out of each side. And if you want to look at this, You can clearly see that it's got that 6-ray star on the top, but as you rotate to the outside of each of these points, you can see that there's a star oriented along several different angles on each of those. And so that's part of cutting the stone, is just choosing where the best orientation is going to be.
A lot of people just want to keep the garnets as specimens, but other people are interested in having them cut into jewelry. And so there are places, there's lapidarists in the area, in the region, that know how to cut these garnets. There is a special technique to cutting them and getting an actual star. One of the lapidarists I know says she can get 98% of the garnets from this site. She can get a star out of. She has a lot of experience with cutting. And so you find a regional and nearby gem cutter, and they can get a star for you if that's what you want. And, you know, in their rough form, you cannot tell if it's going to star or not. And so that's also part of the fun, is just wondering and finding out, if you get it cut, whether or not you got the star. So there's 4-ray stars and 6-ray stars. And of course, the 6-ray stars are the most sought after, but they're all cool.
The garnets from the Emerald Creek Garnet area are like 1 in 2,000 might be a 6-ray.
The best garnets are for sure the ones that have been tumbled and you know, traveled in a stream and then deposited, which tends to, a lot of the garnets up there have fractures in them, and so if you have sort of like a nice, pretty garnet with the, you know, dodecahedron, or the, you know, nice crystal faces and everything, that doesn't necessarily mean it's going to be that useful for polishing, because they'll have fractures in it. So what you really want are the ones that are, you know, fairly, you know, large is good, but also ones that have obviously been tumbled and etched, so that they've already fractured where they're going to fracture. And then it's hard to tell though from the outside, just because, I mean, you can tell whether it's, you know, whether it's fractured or not. But as far as the star goes, it is difficult to tell. And actually, what you want to do is you want to put the base of the stone needs to be one of the parallel to one of the outside crystal faces, and then you dome it over, and the dome needs to be kind of near the middle of the stone if possible. So you're really, you know, you're not going to know about the quality until you've really gotten into the middle of the stone.
The 24s tend to not be very good. They have less definition in the stars in general. So when you see one of those double faceted, you're probably not going to find a star at all. Most of the time, we're not working with a whole crystal, and so it's already split. And so I would just dome wherever it's already split, and that way I'm not wasting material. I'm getting a look and to see what's going on in there. If I do have a whole crystal, then yeah, there is fairly predictable orientations of the star given away by the crystal face.
Why do you see patterns of asterism like this, and then also what appears to be hexagonal? That was always curious to me. And I always assumed if we take a cube, I'm interested in symmetry of minerals, that's what I do, that if you look down this direction, you would imagine if you had lineation this way and this way, that would form the 4-ray perpendicular. If you look down this direction, it appears more like it would be a 6-ray. But I was wrong. That's not the way it worked. The way it actually worked is if we take the corners of the cube, imagine the lineations are through here. So there would be a linear array of these materials, whether they're voids or whether they're rutile, in this direction. So when you looked at it, you could see the different rays as a relationship of the orientation of the crystal, which related back to the symmetry. And it's something when students in geology take mineralogy, most of them hate the symmetry. But it was one of the few cases you could see the external symmetry through the asterism relate to the internal symmetry of the orientation of these lineations.
This is one that I cut when I was in high school. So you can see the star there. And then this other one kind of illustrates the difficulties with garnets, because they're really heat sensitive. It can be heat sensitive, so you got to be careful. This one, you can see some little reflections in there, and that's that's little fractures that probably formed actually as I was grinding it and polishing it. Is when you got to keep the water on it, otherwise keep it cool, otherwise it'll fracture on you.
I just take it to the 3000 if I'm doing a star test, because then I can see it whether it's strong or weak. And like with a strong star, you can see it at the 600. But yeah, I think the 1200 is really where you start, where you like know whether it's going to be there or not.
And this is the grinding setup that actually what I first used was just 2 carborundum wheels, and then a series of plates, sort of like this. Actually, this was on the end of the device, and this would spin, and you'd put different sandpaper grits on it. And then we graduated to this, which is a diamond, which really made it a lot faster. So there's diamonds, industrial diamonds, that are in these wheels here, and it's just coarse to fine.
Yeah, and the oil helps a lot too. If you do, you could probably get away with just doing 600 and getting it wet or oiled.
Put a little bit of oil on it, and then that'll help. You can see into the stone just a little bit better, and I could use actually a little bit more oil than I put on there. But as you're trying to orient it, because what'll happen is if you don't have it properly oriented, the X in that star will be off to one side. And so the trick is to get the X on the top. So.
Yeah, I've only cabbed a couple, and the one that I did cab it's a little bit off.
Yeah.
It was a good size, so
You could adjust it. Yeah. So for I know a lot of them, you're looking good, and then I got to tilt it just a little, so you cut the back a little more, and then after you get done, and now you got half the garnet you started with.
So if I've got a star test, the first thing I would do is look at it. If it's a whole crystal like this with fractures, I might split across the fractures, because it's going to break. I want it to break where it's going to break, so I don't have to waste material. And then what I end up with is whatever largest piece I have. The star, at least from Emerald Creek, the stars are almost always strongest at the center of the stone. So I'll determine where the outside is. I call it the rind. And then I'll just cut on the grinding wheel, just polish a dome onto that inside surface.
Do you dab it up at all, or just go by hand?
I just hand cut it when I'm doing a test. Yeah. So, and then once I've got a nice dome, then you just step down the wheels to get the good polish, and then I can put it under a light and see what I've got to work with.
It does seem like the real milky rutile-rich part is in the middles of these garnets, and there are 2 ages of garnet growth. There's an early age, about 1.34 billion or so, and then a later 1 billion-year-old growth around the outside. And so it may be that early one was when that was more conducive to the titanium being in there.
This is up to a final polish on the test. It's still rough on the back, and you may be able to see, they don't photograph well, but you may be able to see the 4-ray star in there.
Yeah, we can see it.
And then, like this one here's still got plenty of fractures in it, so to go from here to the next stage, I would probably split this again. But I already know what the star is going to look like, so from here I can show this to a customer. We can decide what we want to do with it, and we can have a really pretty good idea of what we can get out of it. So at that point, the next step would just be splitting it down, deciding what we're aiming for, or do we want it to try to orient something so that it shows when it's vertical or horizontal. Like you can imagine, like a ring is presented differently towards the light than a pendant. And so we pay attention to that when we're trying to cut the stone. So we need to know where it's going first. Yeah. When I'm grading them, I typically run, if like from a weak 4-ray star, it's going to price out at like $10 to $12 a carat, and then all the way up to $130 per carat for a nice 6-ray. This one is about 200 carats. Something, here's a more, this is a 20 carat stone. And that's a weak 6 ray, so that's going to be in that, probably in around the $80 to $100 a carat. A medium to strong 4 ray, $20 to $30 a carat. And like a 3 carat stone is about the size of a pea.
It taught me something about something where I was wrong at. Because I always thought the orientation of these were different. And when I was explaining as the scientist to the person actually doing it at the gem shop how it really worked, he just looked at me and went, well, you're wrong. And it's like, I don't think so. So then when I actually sat down and figured it all out, I was wrong. And it was kind of a fun exchange. He knew how to cut them, and I just assumed he was cutting them in certain directions, but he wasn't. So it was fun to work with him, fun to figure it out, fun to understand it for both of us. This would be the crystal structure of salt, table salt. It's in a cube. The crystal structure of garnet is also in a cube, but it's a lot more complicated looking cube. So this is the crystal structure model for garnet. Different colored balls, different atoms. So it occurs in what's called the cubic crystal system. So it has this cubic nature to it. And because of that, that's then we can understand these different stars, how they form as a function of a cube. Because a cube and a 12-sided thing has basically the same symmetry of a, so the symmetry we're sort of used to seeing in, well, sorry for big words, in Cartesian space. I mean, in an orthogonal vector set, whereas most minerals aren't like that. The star sapphire has a hexagonal star, whereas the star garnet, it's not really hexagonal. It's not 60 degrees between all those. I always thought it was until we started working on it. It's not exactly hexagonal, even though there's 6 of them. Okay, imagine a cube. Got the cube?
Yep.
Okay, so this is the corners of the cube. Now imagine if this is the lineation for the either the titanium, the rutile, or a void. So if you look at it, if you look at it like this, that direction, so the stars would form like this, perpendicular to those directions. So as you rotate it around, you see different kind of stars. So in this direction, you'd see stars like that. That'd be the 6 ray. And that direction would be 2. That'd be these. It'd be a 2 ray, 4 ray, like that. But see, the angles are different. And in, let's see, that direction would be the 4 ray where they're perpendicular. So each direction, and if you look at this isn't that paper. You can see if you orient this thing, the bottom one, orient it like that gives you the 6 ray, but the angles between those are not 60 degrees. Mm-hmm. Then if you orient it like this one, like that gives you the 4 ray, which is perpendicular. And then like this gives you the 4 ray, which is non-perpendicular. So that, and those garnets, so that's what garnets would chewed up, that 6 ray thing. The garnet itself doesn't have nice faces on it. Mm-hmm. So that's what they find when they find them like that. That's a good indication they'll have more inclusions in there.
I mean, it can either be forming at the same time as the garnet is growing, and since it's right in the middle, it seems like it would be the very early garnet, that would have enough titanium in there to actually make the rutile. And I'm assuming that it would just be as it was growing. But I guess it's possible also to have, sort of a metamorphic effect where you would grow the rutile, at some later point. But it seems to me it would probably just be, right as the garnet was. Yeah.
The symmetry, like in a star sapphire, the symmetry looking down is hexagonal. So the orientation of the particles are symmetry controlled in a star sapphire, just like in a star garnet. In the star garnet, they're along a different direction. And I think with me and trying to teach all these things, forget about all the geek stuff inside of some crystal, go look around. Like the streaked windshield of the car. That's a wonderful example of asterism. The same with if you have an appliance, like a brushed stainless steel refrigerator, it's brushed this way, but the asterism is this way. So you can see these things in many places. Tiger eye is another example. This tiger eye is actually asbestos, fibers of asbestos that then recrystallize as quartz. So the fibers go this way, the asterism goes that way.
Every year, my husband and I get tickets and we come here and we have fun just like the public, digging out garnets, and we have the whole experience, and it's fun. It's definitely family friendly the way that we do it now. The old days of having to dig 8 feet, no one's going to bring their 4-year-old to that, right? That's not going to be something too fun for a little kid. But the way we do it now, we even provide small buckets for small children so they can enjoy that experience as well. And I love these garnets. I knew about these garnets before I ever came to this forest. I didn't know they were on the Forest Service property. And so when I was hired, after I was hired, I found out that we managed this site, and I was super excited because it was on my bucket list. And now it's really fun to get to be here and help support the site.
Why one was like this, one was like that, and then the other, I can't make my fingers go like a hexagonal. Why they occurred in those directions. That was the fun part for that. And no one had really figured that out. I mean, the person cutting them knew which face to cut them on to get which one, but not really understanding the science behind it. And so that was, and I've written several papers like this where when you're done, there's a period and there's nothing else to do. At least maybe how they form, there may be other things people could do, but from my perspective, period at the end of that paper.